Okay, sections T4 and T5. What we want you to really get out of this is that in the simulations you do in your project and this idea of simulation, what happens is we're given a null hypothesis, and ours was, that proportion was going to be 0.59, and then we're given some alternate hypothesis. Again, ours was greater than. More generally, we could do not equal to. Actually, yeah, let's call it greater than. And what you want to notice in 2.4 and from our project is that what we do every time to check this, and this is the underlying idea, is that based on this null hypothesis, we build a theoretical distribution of what could happen. And typically when we talk about proportions or means, okay, so a proportion is a mean, because you're just counting up a bunch of ones and zeros and dividing by how many there are. Well, that's an average. So proportions really are just averages. When we do those averages, what you've seen in practice from Module 2 was that we get this distribution that's at our hypothesized proportion or mean. It's usually tallest there, and then it gets smaller as you go out to the sides, and depending on the value of n in our sample size, right, how big our sample size is, this distribution as it goes down on either side, is either narrower with a large n or wider with a small n. Okay, but every time in our simulations, we're just building something that looks like this, and then we're asking for our data. So our data come in, say here. Okay, that's our hypothesized proportion. Our data came in here at like 0.7, at 0.69, at 0.63, I think, something like that. But our data come in here, and we just ask, oh, okay, well, how much is over here? What's the proportion over here? And that's our p-value. And then we ask, is that p-value less than alpha? But we do that each time, and that's all we ever do with a hypothesis test, is we build this distribution based on the null hypothesis, and then ask, where do our data fall, our actual observation. And if our data fall way out here, way out to the right or left, then that says, well, that's really rare. Maybe we don't believe those data actually came from this. Right? That's our conclusion. If they're way out here, we say, I don't think so. I don't think our data really came from this, because if they did, this is what it would look like. We'd have this picture. So we're going to say they didn't, and we're going to pick HA. Or if our data are comfortably in a higher possibility, so our p-value is bigger, So again, if the p-value, now notice, see, I'm saying p-value here, but this is p, two different things. So if the p-value is less, then we reject A0, because we say, nah, it just couldn't have come from that. And if the p-value is greater than alpha, then we fail to reject. Okay. And again, every single time, never ever changes. In that way, I would agree with you, statistics can be quite boring because it is that same thing every time. You develop your hypothesis statement, your null and alternative hypothesis. Based on your null hypothesis, you produce a distribution. Now, we in these early stages with the simulation, we actually produce and look at that distribution. But as we do it later, we never look at it. We don't bother looking at that actual distribution, but you want to keep that picture in mind. So we build that distribution. We actually look for our data and where they go, and we find this actual number for our p-value, and then we check whether it's less than or greater than alpha. Okay, every single time, and that's what 2.4 is trying to tell us. Now, so that's kind of 2.4, and you can go back to my videos where I talk about some of these simulations and what we did, and I did that in 2.1, some 2.1 videos, example 1 and 2. And then in 2.5, that is getting at what we do in our project, where we realize that, yeah, when we make these distributions by doing simulation, right, we get our histograms or bar charts. I'm doing them as a bar chart just because it's way quicker and easier for me, drawing like this. But what we learn is that these seem to follow this mathematical thing called a normal distribution. And in 2.5, that's what it's trying to tell us. That's the central limit theorem. It is simply telling us that if we want to look at proportions or other averages, that as we take more and more data, if we look at those sampling distributions, they will look like a normal distribution. That's what 2.5 is saying. And that's all we really need to get out of it, is that that we can use this mathematical formulation called a normal distribution, that we can use that as a nice substitute for doing the simulation stuff. And that makes our life a lot easier, right? Because, hey, this normal distribution, we'll just use a formula. We've got all kinds of tables and things that are based on it. And people have done all our work for us, and technology knows how to work with it, and so forth. So it's just a great thing. Okay, and that's 2.5 with the central limit theorem, telling us what we see in our project, that these sampling distributions that we make from our simulation, well, we could have simply estimated them very, very well using a normal distribution. And so that's what we'll be using from here on out. Okay, so that's 2.4 and 2.5.